So in this video, we will cover the effect of the magnetic field on several conducting cables carrying current. So let's start with this one. So a metallic rod of length L, so this one, and mass M is given, can slide without friction on two parallel horizontal conducting rails as shown in the figure. So the current in the circuit is 2 amps, and the circuit is placed in a region of a magnetic field. Okay. So the question is, calculate the direction and minimum magnetic field for the circuit to become open. So what should be the minimum magnetic field that we can apply in such a way to lift this bar upward? So in such a way that there will be no closed circuit, which means the current will not flow. Okay. So the first thing is, for this to be true, or to happen, so the magnetic force must be upward. Okay, so we have the electric current, okay, and the magnetic force must be upward, which means the magnetic force must be into the page. So using the right-hand rule or any other method, you can easily see that the magnetic field must be directed to the right. So because the magnetic force is equal to I, the length of the cable across B, and the direction of the length is given as the direction of the current. So if you do the current, the vector current here, or current density, times across B, it will give you a force that is going out of the page. So the magnetic field must be directed to the right. So now, what is the minimum magnetic field? So the minimum magnetic field is to provide enough force to beat the gravitational force. So the magnetic force must be at least equal or bigger than the gravitational force. So we know that the magnetic force is equal to ILB, because L is and B has 90 degrees angle. So this means that sine 1 is equal to 1, sine 90 degrees is equal to 1, and the magnetic the gravitational force is equal to the mass of the rod times G. So this means that B, the magnetic field must be bigger than mg divided by L, which if you replace, it will give you 1.4 times 9.8, the gravitational strength, and then the current, which is 2 amps, and then the length of the cable, 0.5, and this will give you 13.7 Tesla. Okay, so this is just an application of the magnetic force applied, or the magnetic force on conductor carrying a current. Let's go to another example. So this example is here. Now we have a rectangular loop. We have a rectangular loop, and it is put in a region of a magnetic field of 2.1 Tesla. The loop is carrying a current of 1.5 amps. And the question is to calculate the net force and torque on the rectangular loop. Now, let's draw it more clearly. So we have we have this loop, and then let's say this is the current is going this way, okay, and the magnetic field is inside the page. Okay, so the magnetic field, and then I will call it side 1, side 2, and then side 3 and side 4. So I will use the reference frame. This is X, this is Y, and J, of course, K will be, Z will be out of the page. So this is I, J, and K will be out of the page. Okay. So the first thing is, what is the magnetic force on side 1? So the magnetic force on side 1 will be, we can see that it's equal to I, L1. L1 is side 1 cross B. So L1 or I is going this way, and the magnetic field is going into the page. Okay, so I is going this way, and the magnetic field is going into the page. This means that the force will be into the direction into the right. So the magnetic force on 1 will be equal to I L1 B and then I. Okay, and then the magnetic force on side 2, well, you can easily see that inside 2 the current is going up, the magnetic field is going into the page. You can see that when you do I cross B, you have the magnetic force going to the left, okay, which means in minus I. So it's the same length, because it's this L1 is equal to L2, so it's equal to a minus sign here, and then L1 or L2 BI. Okay, then let's go to 3, side 3. So F3 again is equal, we know that F3, the current is going this way and the magnetic field is going this way. So if the current I cross B will go, so F3 will go into opposite direction of J, which will be minus I L3 BJ. And then F4 will be the same thing. So the F4, the current is going to the right, the magnetic field into the page, and this means that the force will be upward. So the force F4 will be upward. So it will be I, L3, B, and J. And now you can see that the total force on the loop is 0, because F1 will cancel F2 and F3 will cancel F4. So the net force is equal to 0, and also the net torque is equal to 0. Okay. Now, just let's assume in another case where we have the same circuit, have I here. This is a side 1, side 2, side 3, and side 4. And for example, let's assume I have the magnetic field going to the right, for example. So this is the current. Now you can see that for F2 and F4, those are equal to 0. The forces are equal to 0 because they are either parallel or anti-parallel to, the current is either parallel or anti-parallel to the magnetic field. So for F1, again, I will still keep X, Y, and Z. So F1 will be I L1 cross B. So it will be I L1 cross B, and you can see L1 cross B, it will give you K. It will give you a force that is going out of the page. So it will give I L1 B K. So this guy will have a force that is going out of the page. And if you calculate the force on F on the side 3, it will be I L3 cross B. You can see that I3 is going this way and the magnetic field is going this way. So if you do I cross B, it go into the page. So this force F3 will be equal to minus I L1, or well, L1 and L3, they are the same. L1 and L3, they are the same, B and K. Now you can see that this will have now a torque around this axis. Yes, then you can calculate the torque, because this one will, the force F1 will be pulling the loop into the out of the page, and the F3 will be pulling it inside the page, so there will be a rotation. So basically it will be rotation around this axis. Okay, thank you.